If they don't do population control, the result is going to be a much bigger problem. Right, so let's go ahead and get started. I just got this stuff, this material prepared this morning, so I'm hoping that it will be useful today. All right. So I just added, these 2 pages. The last one is still kind of work in progress. I don't think we'll get there, today, so it's okay. We'll start with what's inside the computer. You probably have not read it because I just got it prepared like this morning, between 5 and 6:30 a.m.
We didn't have the homework due today, do we?
No, we don't have any homework due. You're gonna have to, make some homework and get that stuff running too. But before, let's go ahead and go over this material. Because I just wanted to explain what is inside a computer, okay? And there are certain things, about, inside a computer, and this is a kind of integrated piece. It's not just explaining, what makes up a computer, but there's also another piece that talks about, okay, what happens after you are done with your computer. Okay, so we'll go ahead and get started with this. The first part is, this is by no means a full explanation of how a computer works, or what is even what is inside a computer. To truly understand how a computer operates, a single bachelor's degree is not enough. A single bachelor's of science is not enough, because you can get a computer science degree, you can get an electrical engineering degree, you can get a computer engineering degree. One of those degrees will give you a significant knowledge of how a computer operates, but not enough to tell you everything about how a computer operates. Okay, so this is, definitely an abridged version of all of that knowledge, because I don't understand, 100% of, how a computer operates. At least, not down to the physics device, physics level, but enough to really give you an idea of, in general, how it operates.
Well, with the technology, it's just changing more and more every day, so it's kind of hard to just know everything.
They're pushing the technology, but the basic engineering and science concept are pretty much the same. They have been the same for the past 30 or 40 years.
So no matter how much we progress in that, they'll still be the same?
They're pushing against the limit right now. They're pushing against the physical limits of semiconductor-based digital computers. So they're going to move on to something else, pretty soon. Like over the next few decades, I think there will be some breakthrough in terms of what material they use and what physics, what science they use to build future computers.
Well, like the supercomputer the military uses, how complex is that?
In the military, the funny thing is it depends on the installation. The military sometimes have older computers because they need their computers to be hardened. In other words, in the event of a nuclear blast, the equipment has to continue to function. The problem with nuclear blast, when you're operating electronics, is not really so much the destructive power of the nuclear bomb, which is really devastating, right? You can level buildings, over a wide radius. But the electromagnetic pulse that it generates can destroy electronic equipment over an even greater range. In other words, a small nuclear device can take out, a lot of electronics without actually destroying the equipment, but it can take out the electronics, which renders a lot of modern weapon basically unusable. So the military needed all the electronics, all the equipment to be hardened against radiation and EMP. And that's a process that's why they cannot use the latest and greatest technology, because they need things that are specialized.
Then why do they call it the supercomputer? And
they might have supercomputer centers that is not on vehicles that can be exposed to that sort of thing. So EMP is one big thing that can destroy electronics without actually physically damaging the parts. Yep.
I think for it to affect the greater range, they have to set it off in the upper
right.
atmosphere.
Yeah, they have they do a lot of studies, or simulation of at which altitude to detonate a nuclear device. So it depends on whether people want to destroy ground targets, kick up as much dust as possible, or maximize the shock wave, or do you want to destroy electronic equipment? So they all have optimal altitudes and also yields. It's not always the bigger the better.
Right.
Yeah.
Depends on what they wanted to accomplish with the initial attack.
Right, because if they want to just disable electronic equipment, they don't need to kick up a lot of dust or have a lot of yield, and have a lot of fallout, as a result.
So is the supercomputer the fastest? Like,
I do not know the current super fastest computer. It's I think it's between Japan and China. I don't know who has the fastest now. And with a supercomputer, they can do a lot of fun stuff.
but don't you have to cool it? Don't they have cooling systems to cool it down?
Yeah, they have cooling problems and stuff like that. So they are constantly pushing technology. But once again, we are not pushing. It's not changing the physics. We are not discovering new physics. It's really applying what we already know and improving the techniques to make faster computers. All right. So we'll just kind of move on and talk about sand, glass, plastic, copper, and gold. Okay, and that's pretty much what is inside the computer. Do you guys expect computers to be made out of material like this? I know you can probably expect copper as a conductor. Plastic, yeah, we can expect that. But sand and glass. So we'll take a look at what this is all about. We'll start with the most critical component of a computer, the part that is actually active. In other words, there are parts of a computer that is, it's there, but it's not very interesting. Like the case of a desktop computer, it's made out of sheet metal. You can have all kinds of designs, but nonetheless, it is really just material sitting there. It's protecting the components in the inside, but it's not very interesting. It is not what makes a computer a computer. Okay. Instead of making a case like this, what are some of the other options to make a computer case?
Plexiglass.
Plexiglass.
You can see
Just
inside.
keep it in a big rack.
Big rack,
Sort of
so it's
rack.
kind of like kind of more open-ended.
Just a shelf.
Yeah, they still have a metal case around, just so that things cannot get dropped onto the circuit board. Yep.
I've seen one in like the plexiglass tank, which is filled with
Oil. Yep. That's an interesting one. You can basically look into a fish tank computer with oil in the inside. So here we have,
How is it working with
Lots
the
of
oil
it.
inside?
well, it works really well.
No, I mean, that's not what I meant.
The oil doesn't conduct electricity.
They use, some people use, like regular oil, like cooking oil, which is not really the best choice, because regular oil, they degrade over time. They oxidize and they smell. Okay, so it's not really the best, to use. Some people use mineral oil, and you can also specifically use transformer oil. Now we are talking about not a transformer that you use at home. We are talking about a transformer that serves an entire city block. Okay. And those, transformers get really hot, sometimes, and
You know
then
about like the transformers on telephone poles?
Yeah.
those are considered small. We're talking about the ones that have fans and they're installed on the ground because they're way too heavy to be on a pole. And they have what we call for the lack of a better word, transformer oil, and that stuff is really stable over a wide range of temperature. They can withstand at least hundreds, if not thousands, of volts and not conduct anything in the inside. So they're very stable. And it simply does not oxidize either. So it'll be a perfect oil for something like this. So we'll take a quick picture at this one. Let me see if I can. Yeah, there you go. So it's a fish tank with a motherboard, and the transformer of a computer, the CPU with its own fan and heatsink and everything installed here. Why do you think this works?
Keeps it from oxidizing?
It keeps things from oxidizing. That's good. Actually, I never thought of that point. This actually makes the contact last longer because it's not exposed to air. Thank you.
So when that fan is going, does it make it swirly in there?
Yes, it does.
Nice.
But it has to turn a lot slower because the viscosity of oil is much more than air, right? So you would think that because it's rotating so slowly, it will just kill the motor because it cannot rotate fast. No, because oil carries heat a lot better than air, so you don't need to stir up as much oil when you want to remove heat. Yep, go ahead.
It's similar to water cooling.
In the end, to keep it cool with a setup like this, it has to do with how much surface area this tank has. And also depends on the material on the tank, because if you use a material that is more insulating from, in terms of heat, then you cannot get rid of as much heat. If you use a material that is more conductive in terms of heat, it has a lot of surface area. Yep, go ahead.
I'm a little confused. This is counterintuitive to what I know liquid and motherboards just don't mix.
Well, there are two types of liquids. There's liquid that conducts electricity, which is bad. And there's liquid that does not conduct electricity, which the electronic components is nothing more than just fluid that helps to carry heat away.
So
And in this case,
I'm sorry, so none of this is water, so they're all, it's not...
oh, it's
just
definitely not
regular-
water.
It's definitely just a regular motherboard, regular fan, regular
Yes.
wires and...
Everything is regular except it is not water. Yep, go ahead.
And it's like clear, the motherboard, you can see through it?
Well, you can see right through. The motherboard itself is not clear, but you can see through the tank and actually see the motherboard and all the other components working in the inside, including the fans and stuff like that. Yep.
You got the deals wrong, they don't sell them like that?
I'm pretty sure you can buy one, but people who do this, do it because it is fun to build one.
Not the performance, you know that?
Sorry?
Not the performance,
What kind of performance?
like you said, they build it just for what?
For fun. Just for fun, and also and also for high-end systems, this is actually a more effective way to get rid of heat, because you're using the entire surface area of the tank to get rid of the heat, and instead of just using a fan and try to blow hot air out of it. Yep.
I think I saw the same buttons similar, the mother, it's like everything transparent.
Yeah.
So I can see through, the mother,
Mm-hmm.
the whole thing.
They make plastic cases like that, but not filled with oil. Very few people would do something like this. Now, there is one major problem with a setup like this. It has to do with running the wires into it, because there's a effect called, is it called caterpillar? No, capillary effect, which is kind of the same thing as when you use a tissue paper and dip it in water. The water will seep out all by itself. Okay, oil has a similar effect. It's just a lot slower. So eventually, if you run wires into this tank here, if the wire is, or the wiring is not properly sealed, oil will come out the other end. If you try to run a mouse out of a USB port here, one of the days you will find out, hey, why do I have oil on my desk? It's actually because of the oil just being carried through the USB cable into your optical mouse, and it will just make a big mess. But these days we got Bluetooth, right? So there's no need to run any wire except for the power to the unit, and you can probably seal one end so it doesn't, the oil doesn't go through.
So you would actually have a USB inside the tank. With
Right.
the little-
Yeah, but most motherboards already have USB ports on it, so you can just plug in the Bluetooth dongle to the USB port, and then you can use Bluetooth keyboard and Bluetooth mice, and then you don't have any contact issue with that. Yep.
So no internal hard drive, it looks like, that too fast of a speed.
Right, because
oil
internal
like
hard
that.
drives still need air, for suspending the disk head on top of the platter. So the hard drive, still has to be external to the tank.
Put a solid-
But if you use solid state, you can put it
solid
in.
state in there.
Yep, you can put a solid state in there. Yep.
Another way that some of these guys keep oil from coming out the cords,
Mhm.
you can actually tell the way the motherboard is situated. The I/O would be up,
Mhm.
so the oil level is just below it, so they can plug everything, and then they put their hard drives and stuff just like right next to it,
Uh-huh.
just on that top shelf kind of thing.
Yeah, it has to be pretty high up, because your oil has a capability of crawling up. Especially with smaller wire. The thinner the wire, the more it can crawl up. Yep.
You said the fan in this case is used to disperse the heat. Doesn't the oil eventually heat up and raise it?
Yes. So in the end, it will reach what we call a steady state. The steady state means it has reached a equilibrium. The equilibrium is basically how much heat is coming out of the processor, and then how much heat is radiating from the side and also the top of the fish tank. So hopefully by that time, you won't have too much heat, and the dissipation just because of the surface area will be sufficient.
So something like this, you cannot run 24 hours or 7 days straight.
Sure you can. The average power consumption of a computer is only about 40 to 50 watts. And given the tank of this size, it's the same thing as dipping a 50-watt light bulb into this thing and see whether it will reach a temperature that is quote-unquote comfortable to the processor. A processor can easily operate up to 30 to 40 degrees Celsius, and I think this won't get even close to 40 degrees Celsius in when the room is about room temperature, about 18 to 20 degrees Celsius. So I think it will work just fine for a normal setup. If you have a super gamer setup, it's a different story. Then you have to run a car radiator to get rid of the heat. I'm just kidding, nothing that big, but you still need a radiator to get rid of the heat. All right, so the case is not very, well, okay, I take it back. The case is interesting in this case, but it doesn't really quite, it's not the part that makes a computer a computer, okay? In this case, it's interesting to look at, it is actually functional in a way, but it is not what makes a computer a computer. What makes a computer has to do with the processor and the other electronic components inside the computer. So we'll go ahead and take a look at that part. A modern computer, and of course I have to say circa 2013, because in case someone is reading this 20 years from now, they will say, no, that's not true, we don't have transistors anymore. Okay, so today, we still have transistors. A transistor is mostly made out of silicon, and this is a link. You can go open a new tab if you want to a Wikipedia page on silicon. Silicon is not a very interesting material on its own. Okay, it is a crystal-like material. It is not conductive by itself. It is not even semiconductive. So the whole term about semiconductor has to do with the fact that it is silicon with traces of other elements in it. Okay, that is what makes silicon semiconductive. Silicon by itself is non-conductive. It is very common in sand. Okay, when I did not intend to. Okay, so if you just look up sand, silicon is the 8th most common element in the universe, not just the Earth, but in the entire universe by mass, but rarely occur as pure free element in nature. It is most widely distributed in dust, sands, planetoids, and planet as various forms of silicon oxide, silica, or silicate, and so on and so forth. But it is very abundant on Earth, okay? Because sand has a large component of regular common sand on the beach. A pretty common part, a big part of it is silicon. Okay? Do we have any questions about silicon itself? No questions? Okay. All right, so that part is no big deal. It's nothing really exotic. It is not an expensive material. To refine silicon and prepare that for use in a computer or in any type of electronics, that really does take very specialized equipment. The fabrication equipment used to manufacture chips, ICs, integrated circuits, we'll talk about that too. It's really highly specialized. There are only a few companies in the world who manufactures equipment for that. So we're not too interested in that process. There are two things we have to understand about transistors, okay, especially inside a digital computer. The first thing is a transistor only has two states that we have to worry about. It's either on or off, okay, and therefore binary. Remember we talked about binary numbers, base 2 numbers. We only use zeros and ones to represent values, okay. So that's pretty much why we are doing that. It's because we only want to rely on two states of a transistor, because it is very easy to differentiate. Is it on or is it off? Now, if we want to differentiate, 4 states, of a transistor, it is a lot harder because is it on, is it off, is it halfway on or halfway off? Then it becomes kind of difficult, and errors can happen much more easily that way. And then the other thing that we have to understand is the state of one transistor can affect the state of the other transistors. In other words, you can turn on one transistor, but by doing that, it can turn off some of the other transistors. And that's how they work together, inside the computer. For the most part, for the discussion of this class, you can look at transistors as, well, tiny switches, okay? So you can flip it on, you can flip it off, okay? It's just tiny little switches. So as a switch, they can either be on or off. However, a switch can control or also have an effect over a overall circuit. I can draw a picture real quick here, and this time I'll be careful to use a dry marker board, whiteboard marker. Okay, so let's look at the switches arranged this way. Okay, so with switches arranged in this particular manner, which is called in series. How many switches do I need to close, which means to make a connection, before whatever voltage is on this side can be sensed on the other side?
3.
I need all of them, right? Okay. What if I arrange the switches in a slightly different way? What if I arrange the switches kind of like this way? This is called parallel in physics. Okay. So if I present the voltage here, how many switches do I have to close so that the voltage can be experienced at this side? At least one. Okay. You can close all 3 if you want to, but all I really need is 1. Okay. Does this resemble something that you already know in logic? Logic, I've never taken a class in logic. Well, that's okay. Do you know the English word and, A-N-D? And do you know the English word or, O-R? Which one do you think is and which one do you think is or? The top one is and then the bottom one is or. Okay? So you already know and have used logic all your life already. We just never really talk about it, that way. Okay, so we'll talk a little bit about this some more later on. Okay. All right. So the next part is kind of amazing, because even to me it is amazing because over a period of about 20 years, a lot has changed. Physically, inside the computer, especially on the processor itself, each transistor is very, very tiny. It is measured in tens of nanometers. Nm, lowercase n, and lowercase m stands for nanometer. The n stands for nano, and then the m, lowercase m stands for meter. A nanometer is very small. Nano, as a SI unit, is 1/billionth of something. In other words, you can apply nano to just about anything. You can say a nanogram, okay, which means it is 1/billionth of a gram for mass measurement. You can say something is a nanometer for length measurement. You can say something is a nanosecond, okay, which is 1/billionth of a second. Okay, so nano is nothing more than a scale. Okay, you're just applying that to say, okay, what measuring unit are we using? What is the scale of that unit? A meter is a meter, which is about the same, which is about a yard. Is it longer or shorter than a yard? I think it's just a little bit shorter than a yard. Okay. But pretty close. Okay, if you just look at a yard, it's about this much, and a meter is about the same. So a nanometer is 1/billionth of a meter. Now, by comparison, a strand of human hair has a width of 17,000 nanometer to 181,000 nanometer. Is that?
Could you say that again, please?
A strand of human hair has a width of 17,000 nanometer to 181,000 nanometers. Okay, sure. Okay. I find it amazing. I'm not sure about you, but I certainly find it very amazing that by comparison, human hair is gigantic. Okay. So according to this website, you can if you want to, you can click it too. This is the website where I got the reference. So human hair, is from 17 to 50 micrometer. Now a micro is also a measuring unit. It is 1/millionth of something. Okay, which is 1,000 of a billionth of something. Okay, and that's why I did the conversion for you already, and that's why you see the 3 zeros here, because 1,000 nanometer is 1 micrometer, which is also called a micron. All right. You guys don't seem to be very amazed, so let me draw another picture that will hopefully make you let you understand how amazing this thing is. So we'll take a strand of hair, the thinnest possible strand of hair from a human being, okay, which is about 17 micrometer. Okay, so here's a human. This is the cross section. Okay, so we'll take one single strand of human hair and cut it on the side, so we're looking at the cross section. And according to that website, this cross section is about 17 micrometer, or if you want to convert everything to nanometer, it is 17,000 nanometers. Are we doing okay so far? So, and then you look at the size of a transistor of an i7 processor. An i7 processor has a transistor size of in one dimension. It is 32 nanometers. Yep.
Would a micrometer be the same as a micron?
Yeah, it's also known as a micron. At one point of time, people or engineers believed that they could not make a transistor smaller than a single micron. So anything that is submicron was already considered a miracle. So when we had 700 nanometer or 0.7 micron transistors, they were already thinking, wow, I thought this was not possible. And that was only when I was in graduate school, which is about 15 to 20 years ago. Okay, so 20 years ago, they thought they could not make a transistor smaller than a single micron, and now it is considerably smaller than a micron. Okay, so we have 17,000 nanometers here. One single transistor is only 32 nanometers, which means how many can I fit across this entire thing? 17,000 divided by 32 is what? I think I gave a number over there. I don't think it's 5,000. I probably did the math wrong here. I think it is 500 or 50.
Bust out the calculator.
531.
500. Okay, so I'm off by 1 0. But 500 is still pretty amazing. Let me fix that first, because I don't want to give you guys wrong information here. So we'll go ahead and edit it right away. That's before my morning coffee. Right there. Get rid of 1 0. I don't know about you, but fitting 500 transistors across a single strand of human hair, and we are talking about the finest human hair too, it's pretty amazing. Imagine, one dot from this, whiteboard marker is one transistor. Okay, that's one dot. That's one single transistor. I don't think I can fit 500 of these across this length. In other words, this is actually bigger by scale. This is actually bigger than a single transistor when a single strand of human hair has a cross section like this. And you guys are not amazed? No? Yep.
But eventually, won't Moore's law come to an end physically that you can't fit?
Right. Well, it's not the fitting part. It has to do with reducing the oxide layer of a MOSFET. It's kind of, that part depends on you have to understand technically how a transistor is constructed before you understand that part. But basically, at a certain point, insulators, they are not insulating anymore because it is too thin. Because by that time, you have a single layer of atoms acting as an insulator. And it cannot get thinner than one single layer of atoms. All right. So I think this is pretty amazing. This is why transistors are packed into integrated circuits for manufacturing and utilization efficiency. Because if you have one tiny little transistor like that, and you have to manually hook up all these transistors, to their companions, that would take a lot of work. That's why we pack everything into what we call integrated circuits for manufacturing purposes. An integrated circuit is also known as an IC, which is the abbreviation of integrated circuit. We also call those things chips. Okay, one chip is one integrated circuit. Yes.
You say the transistor has is made it possible to send the signals on and off electricity, right?
A transistor is like a switch, so it can either be on or off.
So in other words, what we're studying right now is the hardware part of the
Yes, we are studying the hardware part.
So once we try to program, which is the software part,
Correct.
we send it through the keyboard, which is the hardware part. The signal switching on has to be connected to those transistors.
Well, to understand software and how it is actually applied, software is kind of like, okay, you look at a transistor, there are two things that you have to notice. One is something that is visible. Here is a transistor, okay? It is physical. You can use what we call an electron microscope to look at transistors at that size, okay? A regular microscope can no longer, an optical microscope cannot see that anymore. Okay, so you have to rely on specialized microscopes to see things that are that small. But when you see it, you cannot tell whether it's on or off, right? You can just see physically that it is there. Software has to do with whether something is on or off, or the actual configuration. Now, this is one part where a light switch is not a good analogy, because when you look at a light switch, you can actually tell whether it's on or off. But when you look at a transistor, you cannot tell whether it's on or off. Software has to do with the state of a transistor, but we cannot see it, not usually.
Because it has a logical signals like IN, that's why.
Because when it's on, it's really just having a certain voltage applied to one end of the gate, and you cannot see voltages unless you use equipment to probe it. And that's why we can see hardware, but we cannot see software, because software has to do with the state of the transistors in memory and also in the processor. So when we get to software, we'll talk about that part. Right. An Intel i7 processor has about 1.4 billion of transistors on a single IC. And that's, I think that's pretty amazing too. I mean, fitting 1.4 billion little transistors onto a single die, that's pretty amazing. That it takes a lot of technology to do that. Do we have any questions at this point? Yep.
I remember watching a show one time and they were saying that light would take over because it would take over the physical barriers of the IC because it can carry more information.
Light has one advantage. It doesn't have what we call a routing limitation. When you design a circuit like this, the routing, which means how do I connect one transistor to another transistor, the routing part is two-dimensional. It's kind of analogous to the highway and the road system that we use. Okay, it's built on a surface, a two-dimensional system. Okay, and that's why we have overpasses and underpasses, bridges and tunnels and stuff like that. Why do we have those things when we are driving in our
Keep traffic moving.
To keep traffic flowing, because without those things, what else can you do to control traffic? Stop signs, right? Because on a two-dimensional surface, you cannot have traffic that is crossing. Okay, you need some kind of control and say, okay, cars going this way can go, and car going the other way perpendicular can have to stop. But in terms of transistors, you can't do that. You cannot just say, I have to stop the traffic one way to let electrons go the other way. Okay, so they have to rely on concepts like bridges and tunnels and stuff like that to make sure that transistors can talk to each other without any interruption. But because it is still primarily a two-dimensional system, you can only have so much interconnection between the components. You cannot really go anywhere beyond that. And when you have computers made out of light, then you bypass that problem because light can go in any direction that you want to. Okay, especially in a 3D crystalline structure, now you can go sideways, but you can also go up and down. And that's why light computers can to a certain degree bypass that limitation. Quantum computers can go even further because of the effect called gosh, I cannot remember the term. What is the name of the term in quantum physics where the state of one thing can affect the state of something else over a certain distance? Sorry? It has to do with the spin state, but the effect of one thing remotely affecting something else, there's a term for that. It's in quantum physics. I have to look it up.
It's not that tunneling effect.
No, it's not tunneling. Quantum remote.
Spooky effect?
Huh?
Spooky?
No, that has to do with,
Entanglement, that's it. Yeah, it's called entanglement in quantum physics. And that will probably even be better than light wave, because that actually has a fairly good distance to it too. But quantum physics is a funny thing, it's funny business in many ways. How many people are taking or have taken a class in quantum physics? Nobody. Nobody. How many people are now planning to take a class in quantum physics? Okay, a few. Okay, very good. It's really interesting because quantum physics means basically it says things are not deterministic. Okay, that's the basic idea of quantum physics. What do I mean by things are not deterministic? Okay, let me bring up a picture that most of you can remember from just science shows and whatnot. Here's a nucleus, and then we got electrons going around it like that. How many people have seen a picture like this of from different contexts? I think we all have seen something like that. Okay, because this used to be the common view of what is inside a molecule, or what is in an atom. We have nucleus, and then we got electrons like satellites orbiting around it. Okay, but this picture kind of implies that the electrons are orbiting in a continuous way. Continuous means if this is the nucleus, okay, and this is an electron, it is just going around in circles. Okay, and a more important thing about continuous means if the electron at one moment was here and at one moment it was here, that means between those two time, it has to be somewhere in between.
Is that would that be the same as how the planets rotate?
Yeah, kind of. Yeah, if you look at it at a macro scale, that's basically what it is. If this is the Earth and this was the moon, several days ago, and this is the position of the moon, today, the moon must be somewhere in between during the days in between. Does it make sense? That's how things are continuous. Okay, quantum physics basically throws a wrench and this whole thing go like, no, that's not true. One moment the electron can be here, the next moment it can be here without appearing anywhere in between. It just pops up. How? That's the way it is.
Well, that's a cheap
there's
dodge.
there's no how to it, but the how does apply to how do people know something about that, right? Because you cannot actually see electrons, but they can use other things to observe the appearance of electrons. But that's the basis, or I wouldn't say the basis, but that's one of the things about quantum physics is the position of things is not continuous, it is probabilistic. It's just, this entire thing has to do with what is the probability of the electron appearing here versus here, versus here, versus here, versus here, versus here, versus here, versus here. And you have to think about this in 3 dimensions too. So now we can have orbitals, basically, where electrons can be at, and the orbitals can have really weird shapes too. they can be discontinuous. Like one of the orbitals. So let's say this is the nucleus of an atom. Okay, an orbital basically means where can the electrons be, okay, or likely to be. An orbital can now be something like this. It's not even continuous. In other words, with this particular orbital, an electron can be here at one moment, and it can be here at the next moment. And it's all based on probability. Nobody can predict where the electron can be at in the next moment. That's one of the things about quantum physics. Yep.
See this confused look on my face? So are you saying that's what this does?
No. I'm just talking about this is quantum physics, but quantum physics will be used to make the next generations of computers in the next few hundred years or so.
Okay.
Nothing that we really have to worry too much about, but I think it's just intriguing. It's a very interesting topic.
So transistors need constant movement?
Well, transistors are very kind of macro-ish, which means it's really just like a switch. You turn it on, you can turn it off.
So it's on, it's constantly running.
Right, it's continuous, right? Until you turn it off, then it's off. You had a question?
Don't they have to design when they get down to this small enough level, they do have to take into account some of those effects?
Yes, they do have to take quantum effects into consideration, particularly what you just mentioned, the tunneling effect, because the electron can go through an insulator because the probabilistic function can go through the barrier, and that's why it can appear. Right, and that's why it can appear on the other side, which means what you think is an insulator is not insulating enough anymore, and that limits how small a transistor can be, and we are pretty much hitting that limit right now.
Can we get the roll sheet?
I forgot. So everybody is present because there's no evidence indicating otherwise. Okay. Now a chip also has some other additional kind of passive components. It usually has a very tough packaging, which is made out of epoxy or plastic. That's what you see when you see an IC or an integrated circuit. We also have tiny conductors conducting pads of silicon on a chip to pins that are exposed to the outside, and this is how you can solder a chip on a circuit board. The pins are typically made out of copper, because copper is the least expensive material, but it has superior heat and also electrical conduction, which means it doesn't lose a lot of electrical potential when you're conducting through it. However, many chips have pins that are gold plated to slow down oxidation over time, so that whatever electronic equipment you're using becomes more reliable. Okay. Now, I also said, right here, even gold oxidizes. It just does that very slowly. Okay. Yep, go
I
ahead.
used to work at a place that rebuilt lasers, and we used to coat, gold coating.
Yep, because it is also very reflective. Yeah, gold is one of the most conductive and one of the most reflective material that we have access to. Those two usually go together, conductivity versus reflective. They go together because what is the other word that describes light? L-I-G-H-T, light. It is an electromagnetic wave. Okay? So as electromagnetic, it basically means anything that is reflective actually has to be conductive, at the same time. At least on the surface, it has to be conductive.
Aren't mirrors the exception?
Mirrors are not exception to this rule because it is not the glass that is reflecting. It is the silverish, metallic material behind it that makes it, reflective. Yep.
So the sun gives us our daylight, our light. So is that electromagnetic waves, like you were saying?
Huge
Yes.
amounts of electromagnetic waves.
Yes, everything. A lot of things are electromagnetic, without us realizing it is electromagnetic.
Like we see the stars in the sky, that's electro.
Yep. All the light that you can perceive is electromagnetic.
Well, I was just like gonna expound upon that. Like, sunspots will frequently mess up with computers or like technology. It doesn't do that as much as it did. Like,
Now that is not electromagnetic wave.
for real. I was told it was.
The sun, when it has those spots, it's basically it flares. Okay, it flares, and it actually flings out plasma. It flings out actual material that travels over space to the Earth.
Huh.
If it's not for our magnetic, the Earth has its own magnetic field. If it's not for the magnetic field that we have, it would actually strip away atmosphere, like what it had done to Mars. We'll end up with a very thin atmosphere without the shield that we have, which is coming from our magnetic poles.
Neat.
Yep. We're kind of lucky that we still got the magnetic core that we have. But solar wind is actual. Solar wind is actually a material that is coming from the sun, but it is also charged. Okay, which means it has a charge to it, positive or negative. It can strip away atmosphere when it gets to the Earth. When it gets to Earth, it will also mess around with electronic equipment because it also causes electromagnetic interference.
What size is the pin? The pin, what size is
The pins? You mean the pins on the actual chip? They are visible, but they can be very, very thin. Which means, if you want to hand solder something, sometimes it is not really that easy because the pins are so thin and they're so close together. You need to have special techniques or special equipment to do it. All right. What about this last point here? Even gold oxidizes. Okay.
All metal oxidize.
Yeah. Well, oxygen is pretty good at stripping electrons out of something else. Okay. So how do we know gold would actually oxidize? Well, all you have to do is to look at the lifespan of CDs, okay, audio CDs. Okay, we talked about audio CDs, a while back, when we talked about, how to capture audio and digitize and put it onto, an audio CD. So now here's my question to you. Okay, let's say you have a really good collection of audio CDs. You try your best, you downloaded everything, converted everything into MP3 so that you don't have to play the original audio CDs. So you keep it in an album, okay? An album, you put it on the shelf, you make sure it's out of sunlight, it's at a cool environment, it's not exposed to extreme conditions. How long would that last? In other words, in 10 years, if you play that CD again, will you still get your music? In 25 years, will you still get your music? In 50 years, will you still get your music? Your descendants, 100 years later, will they still be able to listen to what you listen today? Go ahead. Okay. The answer is, over a certain amount of time, they won't. Your CD will lose its content over time. Even without scratching or physically or mechanically doing any damage, they will lose the content. Okay? Now, if you buy, a CD, yep, go ahead.
Or if it's kept down in like a salt mine where they preserve stuff.
You have to remove oxygen from air. In other words, you have to put in a safe where you purge oxygen by replacing oxygen with nitrogen or something else that is inert. Okay? But why is that happening? What is happening to a CD in 100 years? A regular CD has aluminum in the inside, and aluminum can oxidize pretty quickly. Aluminum oxide is transparent. That's why your CD will gradually lose its content because the entire thing will become transparent. If you give it enough time, okay, an audio CD will become nothing more like just a transparent disc. Yep.
Usually right over it.
No, because an audio CD, the one that you buy from a store, you cannot write over it. The content is there from factory. Okay.
What about we burn the CD?
What about the writable CDs?
Yeah.
They lose their content even faster. Yep.
So how much do you think it costs to make a CD?
To make a
they charge
CD.
you like what, $18-19 to buy a CD, right? Maybe up to $25.
I would say the cost of an audio CD is probably about 50 cents or less. what
Makes
you're
me mad.
what
paying
you're
for the music,
buying,
not the
it's,
disc.
yeah, what you're buying is not the material or the case or anything. You're buying the permission to use it under their conditions.
It's just like buying on iTunes too. Costs just another fee.
Right. It is not the material cost or even the cost of delivering it or distributing it. It is you're buying a permission to use it in a certain way, which is basically including, you can only use it for your own personal purposes. If you have a CD, if you buy a CD and you play in a block party around your neighborhood, that is quote unquote illegal already, because it's no longer personal use. Read the terms carefully, and you will find out what you're not supposed to do with the CDs. Yep. Okay, so that's why when you want to buy something, if you have a album that you really like, you want to go buy the quote unquote gold version of it. Okay, that's what these media companies store. That's how they store the music in the past. Is they have gold CDs. Basically they're CDs, but instead of using aluminum, they use gold. Okay. Yep.
What if you keep them in a hole? Some kind of away from light, away from air.
Well, the tricky part is not light. The tricky part is air. Because air has oxygen. We have about 20% of air is oxygen, and that's how we can breathe. So you have to remove oxygen from air so that the CD will not get oxidized. And there are tricks to do it. You replace regular air with just nitrogen, which is inexpensive. Yep.
So gold in space will not be affected by electromagnetic waves when it bombards the electron. It won't bounce it off and degrade the quality of the gold material itself.
Well, gold does not oxidize in outer space because there's no air to oxidize it.
But yeah, I understand that. But as far as the gold itself, you said electromagnetism is not affected more, so the air affects it more than electro. Or did I misunderstand?
No, electromagnetism has nothing to do with air. That really is just, it's transmitted. It gets picked up by anything that is metallic, okay, and it can do bad things to electronics.
So a CD made of gold will last centuries?
In outer space, it will last until you have space dust, hitting it physically and destroying it.
So that's why the Voyager 1 made a album disc out of gold?
Yeah, well, that's partially why, because because gold is a material that can last a long time. Yep. When gold does oxidize, what is its color? It's transparent. And that's why a gold CD will also lose its content. You guys don't seem to believe me, so let me just look it up. Gold CD lifespan. Longevity, okay, not lifespan. Longevity. There we go. So I might be off here a little bit in terms of the time. The article, Gold Discs Explained. Yep.
I have a question. I got an email from you about the computer information job or work experience.
Yeah.
If you have to have some type of work experience in that field, or if you're just interested to go apply for it.
Okay, let me finish this topic first, and then we'll talk about that one. Okay, so in this case, according to this, they claim the disk lifespan to be approximately 300 years, which defeats the average 25 to 100 year lifespan of aluminum layered disks. So there you go. With a gold CD, you can have about, depending on how long each generation is, assuming each generation is about 20 years, you have about 15 generations before the content is lost. Now you can always re-encode it and store it in some other way during those 15 generations. So you just have to tell your descendants, re-record this every generation, and you won't lose it. But the lifespan of a regular CD, which is aluminum based, is only 25 to 100 years. Now 25 is not that long of a time. right? 25 years, we are now starting to, okay, kids that are born today, I think they have a 25 to 50% chance that they will live to at least 100 years old. So that means, the CD will go bad within 1/4 of the lifespan of a person. I still want to listen to my disco discs. I mean, I don't want to lose that. Yep.
Does that mean like a lot of the CDs now that have been around for a while, that they'll start like degrading the next
Yes.
couple years?
Some are already gone. Because some people don't store that, properly, like if it's exposed to sunlight, or higher temperature, that will increase the oxidation rate because, temperature always helps in chemical reaction, or in most cases it helps in chemical reaction. But here comes a big question. But how does oxygen get into a CD to oxidize the metal? Because the metal is actually sandwiched within plastic. Well, what we think is impervious is not impervious. Plastic, it actually let air molecules go through pretty easily. And that's how you can see, when you have a balloon, okay, when you have a helium balloon, what happens to it? Let's say it's made out of rubber, the usual material. It shrinks, right? And how quickly does it shrink?
Within like 3 days.
Yeah, within 3 days, it becomes like this size,
like
right? Yep, and that's because the hydrogen can actually go through the walls of a balloon and escape, outside. Not hydrogen in this case; it's actually helium, which is already a lot bigger than hydrogen. Okay, oxygen is a lot bigger too, but nonetheless, it is small enough to go through the acrylic plastic into a CD to oxidize it over time. Yep.
That's why there's never nothing really solid that oxygen can't get through. I mean, like, the only thing that I really seen like airtight is like when I was in Cairo, they had like this 2,000-year-old mummy, and it was an actual real mummy in a sarcophagus. They had like an airtight. The case that it was in was like airtight. Now, what stops the oxygen? Because eventually, the oxygen will make its way in, and nothing's like airtight.
Yep, nothing is truly airtight.
So do they every once in a while change it to like another airtight container? Or?
Well, it may be very slow. That's one thing. It may be very slow, but in the case of a mummy, they also use chemicals to stop the decay and stuff like that.
Well, it's not in a vacuum either. There's something in there. It's got argon or some inert gas taking up the space. It's not a really low pressure. Otherwise, I think
Yep, it would just implode. Yep, go ahead.
What about Blu-ray? How long does that last?
It depends on the material. It has nothing to do with the format of the disc. It has to do with the material they use on the disc. You can probably look it up. I don't know for sure. It has to do with the material that they use.
What about a hard drive?
A hard drive would lose its magnetic content I think within only about 20-25 years. You can look up the longevity hard disk drive. You can just look it up and find out. Yep.
How about the altitude and the place that the hard drive is located? Has to do with that altitude, the pressure.
The air pressure.
Yes, I mean.
Well, the air pressure certainly has something to do with it because the higher the air pressure, that means the air molecule is bombarding the surface of plastic harder, and therefore there's an increased chance that air molecule can go through, and as a result, the oxidation will go faster. Yeah. So you want to move your disk, to a higher altitude where air pressure is a little bit lower, but that won't help that much, because it will still happen. You can put it into outer space. That will help. That will help a lot. As I said, until space garbage hits the disk, then it will be shattered, and there's nothing. There'll be nothing left. All right. Next topic. Or subtopic, glass and plastic. Okay, so now we have chips, individual integrated circuits, little components. But how about a motherboard? What is a motherboard, by the way? A motherboard is the printed circuit board inside the computer that is used to hold most of the components. Not all, but most. Okay. All right, so the main board, which is also known as the motherboard of a computer, is a complex printed circuit board, abbreviated as PCBs in the business. The main material is fiberglass, particularly FR4. This is also a hyperlink. You can go to Wikipedia to look up what is FR4 or a derivative thereof. FR4 is a very tough material. It is made out of fiberglass and epoxy. All right. So instead of talking about fiberglass and epoxy, how many people have the experience of laying concrete, for a driveway or a wall or something like that? Okay, some people do. Okay, do you just use concrete? No. What else do you need?
Water.
Water. Okay, but do you put something in the concrete before it's set?
Rocks.
Rocks. Rocks. Okay.
Rebar.
Rebar. Okay, very good. What is rebar made out of? Iron, right? Okay. So why do we need something like that? Or have you seen the construction of bridges or buildings and stuff like that? Most people have, right? So even if you don't lay your own foundation, you must have seen, how buildings or concrete buildings were built. Okay. So they got concrete and they have, the iron, bars. Okay. So why do you think, they need both of those things? Why don't they just make the whole thing out of concrete or iron? Yep.
It creates stability. It's like a skeleton within the thing. It allows
Exactly.
it to maintain the form.
Yep, exactly. One material is good at one thing and the other material is good for something else. Okay, if you just use concrete, to make, let's say, a flat thing, okay, do you think it's going to be easy to kind of do a karate thing and chop it in half? It's actually very easy. Concrete is hard, but only in one way. Okay, concrete is hard against compression, which means if you make a concrete thing and you put it onto a stable flat surface, if you want to crush it, vertically put something on it to crush it, it's really, really hard to crush concrete. Okay, it can withstand a lot of pressure, from in this direction, compressing it. But it doesn't have any tension strength. In other words, if you make concrete into like a pole, okay, into a stick, anyone can break it. In fact, you just have to hold it on one end. Its own weight will break itself because it doesn't have any strength withstanding strength of tension. Okay, you can actually bend it and crack it pretty easily. What about an iron bar?
But if you took a small piece of rod in that concrete stick, you wouldn't be able to break it.
If it's concrete, it's still easy to break. Okay, does anyone do karate or any type of martial art thing? Have you ever tried to chop rebar?
I'm not stupid.
Because it won't work. Because iron bars are extremely strong when it comes to tension. Okay, it's not easy to break like this. Okay, but it is weak in one direction. What is it weak at? It can bend. It will change its shape.
Hot. It gets hot and it can melt when you weld it.
Yeah, well, that's true too. Yeah, but most buildings are not exposed to extreme temperatures up to that point, or they're not designed to withstand temperatures up to that point.
When you bend it.
Yep. Yeah, iron bars, you can bend it, but you cannot break it. And that's why we don't do karate, chops on iron bars. People have done it on bricks, right? You can watch a lot of the karate shows or martial art of any form, and they would do a headbutt on, like a pile of bricks and break that stuff. But that brick is not reinforced with rebar in the inside, because if it were, you probably don't want to try that because it won't break. And it's the same thing with circuit boards. Okay, the circuit boards inside the computer is basically the same thing. Fiberglass, which is literally fiber made out of glass, is like the rebar. Epoxy is like concrete. So when you only have one material, it's only strong in one way, but it's not strong the other way. But when you combine the two, the combined material, which is called FR4 in this case, the 4 stands for something that I forgot, but FR stands for fiberglass, I guess reinforced. Let's look it up. FR4 is a grade. It doesn't quite explain how the name comes from. Properties. It doesn't say, but anyway, but FR4 is strong in both directions, so it's really durable. Has anyone tried to break apart a circuit board? Did it work?
It's a little harder than I thought it would be.
Yep, it is very hard. Has anyone tried to saw, or try to cut open a circuit board?
But I got tired of trying to break it.
Did that work? Cutting it? No.
I remember this.
Sorry?
Take a sledgehammer to
Take a sledgehammer to it. It will work.
it. It'll shatter it.
It can shatter it, but that's by applying a lot of impact to it. Yep. But it's much stronger than it looks. Okay, you look at a circuit board, you look at it, go like, yeah, it's only about yay thick. How strong can that be? It's stronger than most things of that thickness. Okay. Are there any questions about FR4 as a material? Nope. Okay. Now, if you have never done it before, don't do it. Do not try to use an electric saw to cut FR4 material. Does anyone know why that would not be a good idea? What happens to all that fiberglass when you try to take a circular saw to it? It becomes dust. Okay, it doesn't just break apart. It becomes very fine particles that will float in air. What happens when it goes to your lung?
Like
But unlike regular
glass.
dust, what does it do? What does fiberglass do when you have it?
up.
No, it doesn't cut you up. No,
Fiberglass is
not
like,
when it's small enough to breathe in.
It's an irritant.
It's an irritant and it stays there forever. It doesn't break down. It doesn't break down, it just stays there forever. And to some people, that can be very irritating. So you don't want to breathe in FR4
So what do
dust.
they do like with old computers or whatever when they're recycling them? Do they just melt them down, reuse that?
We have that topic a little bit later. In
Oh,
fact,
okay.
we might have enough time just to go talk about that. Yep,
Are you gonna pass it on also?
I forgot. Yeah, somebody asked it already. All right, so let's go skip, we'll skip copper and gold, okay? Copper, obviously the wires are made up of copper, and then gold, we use, we use gold for all the contact points. So on a good motherboard, when you have like the memory chips, all the contact points for the DIMMs, which stands for dual inline memory module, those are all gold plated, because it doesn't oxidize easily. Okay, so here's a little sidetrack, recycling electronics. What happens when this computer right here becomes so old that it is obsoleted? In other words, it's not even worth to keep it around here.
Donate it.
We donate it, okay. So what if nobody is taking that as a donation because it's way too old, okay? Nobody wants to use it.
E-waste.
It becomes e-waste, okay? That's very good. Okay, at least we know it is called e-waste, which means we don't toss it into the landfill, okay? Now, why don't we toss it into landfill?
It stays there forever.
Hmm?
It stays there forever.
It stays there forever, just like baby diapers. Yes, baby diapers also last forever, but baby diapers have no value whatsoever otherwise, right? So that's why you put it into landfill. But this stuff is actually worth some money. Okay, e-waste is worth some money because of all the metal and all the other material inside. Okay, so we don't want to put it into landfill. Putting something into landfill can be expensive as well. Didn't I talk about how garbage in San Francisco has to go all the way to Livermore or Yuba City? So that's why we don't want to put stuff in landfill unless we absolutely have to. Okay, so as e-waste, yep, go ahead.
Companies that recycle cell phones make a good portion of money off of the gold that goes inside.
Yep, they can get money from the gold, from also the other material too. So e-waste, is good business for some people. So what we want to do is to kind of skip this part here. Is how do we get all the useful stuff out of e-waste? In other words, I take this computer apart. I look at the printed circuit board with a processor on it. How do I get all the aluminum, all the gold, all the other metals out of this thing so I can reuse, I can sell all that metal to somebody else? Well, the first and the easiest way is to burn it. Okay, because when you burn it at a higher temperature, all the plastic stuff will be gone. Well, but it's not really gone. Where does it go?
Into the air.
Into the atmosphere, right? But it's atmosphere in China. Why do I care? Because we are all, Yep, exactly, because we are all living in a big fish tank. Something happens, far away, will eventually find its way back here, and we will talk about how quickly it will find its way back here too. Okay, so at different temperatures, different metals will start to melt. Just physically, it will just melt down, and then can be collected for for further refinement. Okay, so that's one technique. The other technique is to use different types of acids, oxidizers, and other types of chemicals to dissolve metals and other components. This is sulfuric acid. Sulfuric acid is not only an acid, but it's also an oxidizing agent when it's concentrated. So you can apply that to certain material, certain metals, and extract the metal out of it. The last part here is once you dissolve metal using acid and some other things, how do you get the metal back? Well, you just apply electricity, and you can reverse the process. Okay, and that's how lead acid batteries work. Is when it's discharging, it's actually converting metallic lead into lead ion that is dissolved in the sulfuric acid. When you're charging a lead acid battery, you're reversing the process. So you're basically putting the lead back onto the plates, the plates in the car battery. So that's basically the process that people can recover metal if they choose to use this method to get the material out of a PCB. Yep, go ahead.
What kind of battery were you talking about? What kind of battery were you referring to? Just now?
Lead acid battery. The typical really heavy battery that you put in the car. Yep. The rest of it is basically trash. So we are talking about burning stuff and using a lot of chemicals and stuff like that. So we can potentially have a lot of waste, right? A lot of nasty stuff in the process that can come out, and if it's not controlled, it will be released into the atmosphere, into the landfill, into groundwater, and so on and so forth. So let's go ahead and click this link here, because I want to show you some pictures. Okay, so here we have typical recycled computers waiting to be recycled. And then we have pictures of disassembling, collecting, into components. Okay. And now we have, places, that is done a lot, where electronic waste is burned and disassembled with no safety or environmental considerations. Well, but still, this is, some other place, how long would it take to come back here? Yep.
Burns like that and don't think about environmental effects like that. They not care, or they just like.
They don't have the regulations that we do here.
There are several things. There are many factors that I have. Some I have outlined here. The main part has to do with the living standard in some places is very low. Okay. If it's not if it's not worth recycling, they just dump it somewhere. It's not a safe way to dispose of the material. Yep.
Some companies out there are going to try to find the cheapest way to do stuff.
Cheapest way in the short run, yes. In the short run, it is the cheapest way. But mostly it has to do with the living standard of some places is very low. So that's why they'll just do it whatever they want, because if they get something out of it, it's already worth the effort to do it. But it's also because they don't know the long-term effect of these toxic material. Okay, nobody told them if you keep doing this for 10 or 20 years, your river will be completely polluted, and whatever natural resources is in the river will be gone. Okay, if you keep doing this for a long time, not only the river but groundwater will be so polluted that you cannot really grow stuff anymore, and a lot of the natural resources will once again be lost. Nobody told these people of the long-term effect of doing this. Okay, now before we end this class, there are two things I want to address. What you just brought up a little bit earlier, but let me finish this part first. I just want to kind of focus on this part. Okay. When the recycling process is not done correctly, the result would be toxic recycled material. Okay, so if you just kind of think about all the toys that you buy from, let's say, the Dollar Tree, or all the inexpensive toys that you get from McDonald's and stuff like that, How much do you know about all that plastic that go into those toys? Not a whole lot, okay? What if it is made out of recycled material, like the case of a monitor that was recycled? By itself is not a problem, but what if in the process, some toxic material in the recycling process get mixed into the plastic? Now we are talking about something that is toxic, okay? So a lot of toys, a lot of plastic things, especially the shiny type, may have toxic components, so you got to watch out for that sort of thing. Yep.
The manufacturers check for that if they're getting recycled material from some place, or would they not know where type of recycled plastic is coming from?
It becomes very hard to track the entire thing because we are talking about you're talking about many different steps in the process, and you're also talking about countries who may not have the regulation or the means to monitor what material get generated by what facility, where does it go, and eventually track its way into toys and other things. So by the time it gets here, when you get that toy from McDonald's, it becomes nearly impossible to track down where it came from. Okay, so I do want to bring this up one more thing. I sent everybody an email about an opening, which is the city of Roseville. So you really want to contact, if you want to know more about this, you want to contact this person, which is actually an ARC person. The phone number is here, and then the email address is there. So that would be the best person to contact, because this person is on campus, and they will help you through the process of applying for that job. Yep.
What kind of position is that?
It's a student internship. I sent an email to the entire class. The city of Roseville is opening a college intern 1/2 with an emphasis in IT. The job is open on Thursday and is paid internship up to $13.35. So just read the rest of the email. You should have received a copy of that already.
Yeah.
Okay. All right. All right. So that should end today's class. I will prepare additional stuff for Thursday. Yep, go ahead.
What's intern 1 and intern 2?